So far, we've been using let bindings as immutable identifiers for our values. However, sometimes we need to be able to mutate these identifiers. In such cases, we would like to use them just as we are using variables in imperative programming languages. And we can achieve that by using the so-called reference. Let's take a look at variables in JavaScript first. Number is a variable name which is initialized with 5. As you can see, we can mutate this identifier using the equal sign and add 5 to it. However, we cannot do this in Reason because its let bindings are immutable. Nevertheless, we can use mutable record fields to achieve similar behavior. We defined the record type X, which contains a single field called number that is mutable. Then we defined our record where number has a value of 5. And we also modified record's number field using the dot notation and the equal sign. By doing that, we increased the value by 5. So the number's value is now 10. This behavior is similar to the previous JavaScript example, where we used the equal sign to modify the identifier. However, using a record to simulate variables in Reason is unnecessary verbose. Fortunately, Reason provides us with a predefined function called ref, which we can use to create the so-called reference. And this reference is based on the same idea as the mutable record. As you can see, the ref function expects a value of any type and returns a reference. Let's take a look at an example. We passed an integer to the ref function and got back a reference. And we stored this reference as the X identifier. This reference is a cell containing our integer value. And as you can see, it's a mutable record. Let's now mutate our reference. We used two operators to modify our value. We used a colon and an equal sign to update the content of the reference by adding 5 to the original value. And we also used the caret symbol to read the content of the reference. And the compiler returned unit. This means that this modification operation is a side effect. We can now check the value of the X identifier. As you can see, we are using the caret operator to read the content of our reference. We modified our value because the value of the reference is 10 now. Reason forces us to be explicit about these mutations, And that's why we need to use these special operators to read and to modify the content of the reference. So in this example, we use the reference to simulate the variable in Reason. In some cases, we won't need to use the ref function, since we will be able to achieve the same result by reassigning the lead binding. We defined the Y identifier, which holds a value of 5. Then we defined a new version of this identifier with the value of 10. Finally, we check the value of Y. As you can see, the newer definition of the identifier overrides the older one. So the value of Y is 10. In one of the previous sections, we used a reference together with the while loop. This while loop will iterate until this condition stops being true. And this is the situation when the Y identifier will be bigger than 8. When this happens, the loop will stop and the value of the Y identifier will be 8. At the beginning of this example, we initialized the reference with a value of 0 by calling the ref function. And we stored this reference as the Y identifier. We needed to use the reference inside the loop's condition as well, because we cannot compare a reference with a number. We need to have the same types for the comparison. In the loop's body, we modified our reference using the special operators. So each loop's iteration, the value of the Y identifier will increase by 1. And this will be happening until the loop stops its execution. Let's use the reference and the while loop in the more complex example. We defined the division by 4 function, which expects an integer and returns another integer that will tell us how many times we can divide the past integer by 4 before our result is lower than 1. In the function's body, we are using 2 references. We use the first reference as a counter for counting the number of divisions by 4 that already took place. The second reference holds the result of the last division. During each loop's iteration, both these references will be modified in place. When the result of the last division is lower than 1, the loop will stop and our function will return the number of performed divisions.